Hello, today we're going to have another little look at the introduction of the trig graphs that we've been working on the last couple of days. So the three graphs that we'll be looking at are sine, cosine and tangent, and they all come from the unit circle which I've got on the screen here. I've also got a link at the bottom of the page for a Desmos calculator which allows you to kind of have a play with them and see in reality, as you move the point round the circle, what happens with the graphs. I've linked that in your assignment as well, so have a play with that as well. But go through the rest of this video first and then go back and have a fiddle with it, and you'll be able to see some of the links. So I've got SOHCAHTOA written down here, which you'll all remember from previous times. Whenever we have encountered a right-angled triangle, we've tended to use SOHCAHTOA to help us decide how to solve it. In the unit circle, anytime this point here at the top of the radius moves around the circle, it always creates a right angled triangle along the origin here, along this line. And because the length is 1 of the radius, it works out that the height of the triangle here works out as the sine of the angle, because of opposite over hypotenuse, but because the hypotenuse is just 1, and the opposite just ends up being sine of the angle. And the same for the cosine for the adjacent angle, for the A part. And then tan, TOA, becomes the opposite divided by the adjacent, which is sine theta divided by cos theta. Now this diagram that I've pinched shamelessly from the internet has theta. And some textbooks and some questions you've got will use that letter. Most of the time we'll use x. It doesn't really matter. What it means is this angle here that we're not sure what that is, that's the angle that we're talking about, and everything is related to that angle. Okay? As said, once you've finished watching the video, go and have a play with the calculator. It's a graphics calculator, gives you instructions on it on how to use it, and it's quite interesting to see it because you can actually then see things and adjust them yourself and see what effect it has. Okay. First thing I'm going to look at is the sine graph. So that is based on the opposite of that triangle we just looked at. And as the radius of the circle moves around counterclockwise, as the angle gets bigger, which is along the x-axis here, goes through from starting at 0 to 90, 180, 270, 360, gives it one full revolution, and then the whole thing starts over again, because the circle just keeps going round and round. The sine graph is a wave that starts at the origin at 0, 0, and goes infinitely far in both directions, in both positive and negative. It never ends, it just goes on forever. Okay, so that's an interesting place to start. This amplitude of it, when it's a standard sine graph, is 1, which means it goes up to 1 and down to -1. And the standard sine graph is centered around the origin, so it just goes up 1 and down 1. And it just keeps on doing that forever. We talk about the wavelength of the graph, and that is the length until it starts to repeat itself. So it carries on going forever, but once we get past 360 degrees, it starts doing the same thing again. You can see the shape's the same. And the same when we go to the left, past 0 into negatives, you can see that it's starting to do the same thing that it was doing if you had started at 360 and went to the left. It just keeps on repeating itself. Okay. Now, let's have a look at what we can do with that knowledge. So there's a couple of different things we can do. Sometimes you could get a question that asks you to find the value of y, and it'll tell you what angle it is. So in effect, what that is doing, if I go back to the first page, in effect what that's doing is that's telling you this angle here was 25 degrees, and it's asking you how tall this green line is. That's pretty straightforward because we've got our calculators and they are good at these. All you do is you type this sine 25 into your calculator, and it will give you a great big long number with loads of decimal points, which is y equals 0.422, and it just keeps on going. I'm just going to round that to 2 decimal places, 0.42. And I've got no units on here, so it's just 0.42. That means that at approximately 25 degrees, well, exactly 25 degrees, which is going to be around about here, if we went up, that would come to 0.42. That looks like it's about 0.4, so that makes sense. Okay, the next one. This one's a little bit trickier. It's asking us, solve sine of x degrees is equal to 0.6. Now what that means is, what value of x degrees will give us 0.6? So going back to our circle, if it's asking us what value of theta or x will make this green line here 0.6, that's what we're being asked. So we do similar to what we've done before. X equals the inverse sine, x degrees, sorry, of 0.6. You put that in your calculator. You normally have to press the shift and then the sine button to get the inverse sine. I'm sure you've done that before when we were doing right angled trig before. And that will tell you x degrees equals 36.869, and what's other ones, so I'll round that to 36.87 degrees. But that's not the whole story. We have to do a little bit more. So I'll go in blue with this one. So if we think about on our graph, if we figure out where 0.6 is, I think it's going to be right here, and we draw a line. It's going to hit the graph once there, it's going to hit it again there, and then we go right along. That whole blue line would be y equals 0.6. I'll label that up. Y equals 0.6. And then we only need to go to the 360 degrees because after that it starts repeating itself. But what that means is we're going to have 2 possible solutions. One here, where it crosses the graph, and one here, where it crosses the graph. So we're going to have one answer, which is between 0 and 90, as the graph goes up. And we've got an answer for round about there, 36.87, so just before the 45, that makes sense. But we've also got this other answer, it's over here, and that's on the way back down. So, because this is symmetrical from here to the 180, about the 90 degrees, what we can say is that this distance from here to here is going to be the same as this distance from there to there. So our other solution, just like with our quadratics, we have 2, so your x is either 36.87 or it's 180 minus 36.87. When you put that in your calculator, you get 143.13 degrees. So that is our 2 possible solutions that would give us an answer of 0.6. So if you type in sine of 36.87, it'll give you 0.6. It'll give you slightly different because I've rounded it. And then if you type in sine of 143.13, it'll give you 0.6. Again, it'll be slightly different. It'll be a tiny little decimal point difference because I've rounded, but it'll be very close. And that's your 2 solutions. What about if we have sine of x equals a negative number? So sine of x equals minus 0.4 here. So I'll draw my line again and we'll see what happens. So 0.4 is going to be just above the 0.5 there. So we'll draw a line along. And also, I'll draw it this way as well. Because the first thing we're going to do is the same as we normally do. You take the inverse sine of it. Remember that there's a negative there, So inverse sine of negative 0.4, and that comes out and gives you a negative answer. Minus 23, and I'm going to round it to one decimal place this time, minus 23.6 degrees. Now, our graph only goes from 0 to 360. So how can we have minus? That doesn't make any sense. What your calculator automatically does is it gives you the closest solution to the origin. Now, if our graph continued, it would have went back down this way, there. So that has given us this solution here. But that's not one of the solutions we want. But what it does do is it tells us that, in effect, that's also this solution over here, nearly 360. So we're going to have a solution here, and we're going to have a solution here. So this 23.6 becomes the bit that we adjust by. So our answers are either going to be 180 plus that 23.6, because we have to go past the 180 to get to this point here. So 180 plus 23.6, that's supposed to be a 3. So 203.6 degrees. Or it's going to have to be 360 minus the 23.6, because we're going to have to go back from 360 to get to this point. And that is going to be 336.4 degrees. And that makes sense on our graph. The two solutions match where we would expect them to be. So if we typed in the sine of 203.6, it's going to come out at 0.4, or net minus 0.4. And the same with the sine of 336.4. So as long as you understand the shape of the graph, you'll be able to understand what kind of answers you're going to expect and what's going to make sense. So if you had put that in and you had an answer that was about 45 degrees, but you're looking for a negative one, it wouldn't make sense because that's a positive position. Okay. Now let's have a look at same for cosine. Adjacent over hypotenuse. Because the hypotenuse is 1, it ends up being the cos of the angle. And effectively, the bigger that angle is, the shorter that line gets until it gets to 90 degrees. Once theta is up here, and then once it goes beyond, it starts to get longer again. And as the point comes all the way around, once it gets down here, the length of this line here, the yellow one, is back to 0 again. So you'd expect that to be reflected in our graph, and it is. It starts off with the length being 1, and then gradually gets shorter. So at 90 degrees, the length is 0, to minus 1, back to 0, and then up to 1. Now the fact that that goes through 0 in a couple of places there, and the sine one goes through 0 as well, that actually impacts our tan result, but we'll see that in a wee second. Cosine also has a wavelength or a period of 360 degrees, so beyond 360 degrees it starts to repeat itself. And the standard cosine graph has an amplitude of 1 degree, so from 0 to 1, and from 0 to minus 1. Okay. Again, same sort of thing. So to solve the first one, dead easy, exactly the same as what you've been doing before. Type it in your calculator, and it will give you an answer. When you put it in, it comes out at 0.707. Now, cos of 45 actually comes out as an exact value, but we're not going to be going on to that yet. So don't worry about it, we'll just leave it as a decimal, and I'm going to round it to 3 decimal places there. Makes sense? Cos of 45 degrees here, and it's halfway between the 0.5 and the 1, so 0.7 makes sense. Okay. To solve cos of x equals 0.5, we take our inverse cos of a half. When we do that, we get 60 degrees. But again, we have to think about a shape of our graph, and is that going to be the only solution we have? So 60 degrees, cos of 0.5, so we already have a line there. So we would expect the solution to be here, and then another one over here. Okay, so the first one from 0 upwards, and then from the second one, 360 backwards. So our other possible solution is going to be back from 360. So it's 360 minus 60, 300 degrees. And again, that fits what we know about our graph. Okay, what about if we have a negative value? So if we have cos of x degrees equals minus 0.9. Okay, so a couple of different things you can do here. First thing I would probably suggest doing is just drawing the line so that you have a wee think about exactly where you're going to do it. It doesn't have to be a perfect sketch, but I always find it helpful to draw a little sketch. So negative 0.9, just going to be round about here. So we're going to have two possible solutions. One roughly here and one roughly there. Okay. Now, when you have negatives like this and you take the inverse of them, your calculator tries to do some funny things. But because we're trying to find this other solution, something we can do that actually really helps. We can take advantage of the symmetry. So cos minus 1 of minus 0.9. So the shape of the top half and the shape of the bottom half are exactly mirror images of each other. So what you can do is if you take the inverse cos of 0.9, I'll just put this in brackets at the side. So that's at positive 0.9. When you put that in your calculator, it comes out at 25.8. 25.8 degrees. And what that's doing is that tells us that to get from here to 0.9 took 25.8 degrees. What that also tells us, because of the symmetry of it all, is that this part here from 180 back is 25.8, and this part here from 180 forward is 25.8. So our two possible solutions to the inverse cos of negative 0.9 are either 180 minus 25.8 or 180 plus 25.8. So we have 154.2 degrees or 205.8 degrees. And when we look at our graph, those answers make sense. They're in the right place. Okay. Right, finally tan. So tan's a wee bit different, slightly different shape. Well, dramatically different shape. So the tan from TOA, remember that is your opposite over your adjacent. In this case, opposite is sine, adjacent is cos. So let's have a look at that. So TOA. So tan of x degrees is the opposite over the adjacent. But we know, as we've just looked at it, that is the sine of x over cos of x. So tan x degrees equals sine x over cos x. And that's fine. That works beautifully. Let's have a think about what happens with the sine graph. So the sine graph starts at 0, and then it goes up to 1, and then it comes back down to 0 at 180 degrees. And that's reflected in the shape of the tan graph, because 0 as the numerator means that it's 0. So we have 0 at 0 degrees and 0 at 180 degrees. That makes sense because of the numerator being 0. Now let's have a think about the cosine graph. It starts off at 1 and then it starts curving down. When it gets to 90 degrees, it's 0. Now, we have a wee problem because that means that the denominator is 0. We can't divide by 0. It's mathematically impossible. So it's classed as undefined. If you put it into your calculator, it'll come up and say error. And that's why you end up with this little dotted line. It's called an asymptote. And all it means is that as you're dividing by a smaller and smaller number, tan gets bigger and bigger. It goes up infinitely high until as it gets closer and closer to 90. Well, it's exactly 90. It's undefined, so you just get this dotted line. And when it goes beyond 90, it starts being a negative number. And then what happens is it's really close to 90 degrees. So it's away down here at minus infinity, and then gradually comes back up, and then shoots away up into the distance again, because cosine gets back to 0 at 270 degrees. And what that means is that the tan graph actually has a shorter wavelength and a shorter period than cosine or the sine graph, because it starts repeating itself once it gets to 180 again. You can see that it's doing exactly the same shape. So the period of the tan graph is only 180 degrees, but it's got no minimum and no maximum value. So there's no limit to how large the number can be, or small, or how negative it can be either. Okay, let's put that into practice. So we've got a couple of things, or 3 things on the screen here. So the first one, nice easy one, solve y equals tan of 70 degrees. That's straightforward. You just type tan 70 into your calculator, and it tells me that y equals 2.74, and then loads of other numbers. So 2.74, it should have been rounded to 2.75. So y is 2.75. And if we think about that, 70 degrees, it's nearly at 90, so it's going to be getting up here somewhere. It's getting higher quite quickly. Solve tan of x degrees equals 1.2. I'll get my wee line out again, because we're going to have multiple solutions for this. Because even though the wavelength is only 180 degrees, we still look at the first 360 when we're looking at solutions. So 1.2, slightly above the 1. I'll draw my line across here. So I would be expecting a solution here, and a second solution here. Okay, so that makes sense of where we're at. So we do our inverse tan, x degrees equals inverse tan of 1.2. And that comes out at 50.2 degrees, which fits roughly. We're just past halfway between 0 and 90. That makes sense. Okay, and the next one, we're starting off at 180 and we're moving to the right a bit in the same shape as this. So it's going to be moved to the right by the same distance. So it's going to be 180 plus that is for our other solution. So our x equals 180 plus 50.2 degrees comes out 230.2 degrees. So that's our 2 possible solutions, and again, that makes sense. It's just beyond halfway between my 180 and my 270. Now let's have a look at the negative version. Same sort of thing. Tan of x equals minus 1, so we draw a line at minus 1. 2 possible solutions. One here, and one here. Okay, so inverse tan of 1, we can use the same kind of little trick that we looked at before. The inverse tan of -1, if you put that in your calculator, it tells you minus 45 degrees. So that's again because it's trying to give you the closest one going backwards. So what you're better doing is sticking with the positive equivalent. So because all these are symmetrical, you can look at it and just do tan of 1. So I'll just put that across down right at the side here. Inverse tan of 1. And that, when you do it, is 45 degrees. So what that's telling us is that's displacing from the origin, in effect. So it's moved to the left from the origin by 45 degrees. So we're going to move from the left from where it crosses the origin, the x-axis. So the first one's going to be 180 minus 45. And then the second one is going to be 360 minus 45. Because this, I've just not, that should carry on there to 360. So 360 minus 45 is your other one. So that means that x equals 135 degrees or 315 degrees. Okay, hopefully you can see how understanding the shape of the graph and potentially just drawing a little sketch of the graph and then just drawing a little line on it can really help you get your head around what sort of values you should expect for your answers. So that once you get to put something in the calculator, if you put something in and it doesn't fit what your graph is telling you to expect, you know that you've done something wrong. Okay, hopefully that's helpful.